Today is a big day for Owen. Owen came to UVM 5.5 years ago, and he finished his undergraduate degree 4 years ago, then joined my group, and he has been working on his thesis about 4 years. And this project he has been working on is a NASA-supported project, and then you can see the project is quite a complex project. Involves essentially experimental part as well as computational part. Okay. So today we're going to listen to his presentation first, then please hold on a question at the end of his presentation. Then after he answers all the questions, the committee member will stay and continue QA session, and then we will decide the future of Owen. All right, Owen, yours.
So for my proposal, I talked about mostly just some nonlinear dynamics of some charged particles interacting in a particular type of driven system. This time I'm going to cover that as kind of a context for the more recent work, but I'm going to spend a little more time focusing on some interesting properties of long-range interactions, which I'll define shortly. So the type of driven system we studied was what we call the spatiotemporally periodic potential. That's the form of the potential. And so just what does that mean? Those are kind of unnecessarily fancy words for a simple idea, which is a potential that's separable into something like this. So you have a function that's periodic in space and a function that's periodic in time, and this is the relationship we're interested in because there are some particularly interesting features of this. And this is a well-studied system in several different contexts. But just so we know what that words mean, and then I don't want to say those words again, so I'm just going to use this acronym, STP. So yeah, we'll motivate why this is interesting, and we'll talk a little bit about some of the previous work, which was some of the nonlinear dynamics of single particles and multiple particles. And then we'll move on to the more recent work, which is on the nature of the statistical mechanics of some of these interactions, which are very simple. And then we'll kind of tie everything together into a cohesive story. So this started by looking at and trying to understand what's happening when particles are driven by an array of electrodes embedded in some surface. This is a device known as the electric curtain. And it has this STP feature. So the potential above this surface looks something like this. And you can see the form of the potential is periodic in one spatial direction. And then we drive it in this way, where we have maybe some periodic, maybe a cosine of omega t, something simple or more complicated, it doesn't matter. And that gives us an electric field above the surface that oscillates in time and looks something like this at a given time. So the black goes to white, the white goes to black as you go through half a period. And why were we studying this? Well, so cleaning charged particles off of surfaces can be difficult because they can have a large electrostatic adhesion force. But if they are highly charged, then they also interact strongly with an electric field. And so it makes sense to use that to your advantage. And it turns out that this device really nicely can clear charged particles off of surfaces. So in extraterrestrial environments where you can have particles with large electrostatic charges, and one of your only sources of renewable energy is solar, you want to be able to clean your solar panels. This is essentially the first motivation. This device is also used in a variety of other contexts, one being controlling and manipulating red blood cells in solution, transporting liquid droplets on a surface, the separation of particles by their charge to mass ratio, which might be useful for some industrial reasons, And I just want to show a video of some of the work we've done with the cleaning and mitigation of charged dust, which we've shown here the solar panel output voltage, which is below as a function of time for several different driving frequencies. These are in hertz. And basically, this is an interesting video, but it's a complicated problem because you have this particular type of driving, and then you have all of these particles that are charged interacting. And so we took some high-speed videos of these to try to measure things like the velocity distributions to see if for certain driving parameters you can impart the most kinetic energy and have a good clearing efficiency. And then we started to look at some more random motions, but we also saw that there are some interesting dynamics that occur in these systems. And so the dynamics hadn't really been very well investigated, so that was kind of what we started with. And those are videos I had shown. So we also simplified the problem because this particular form of driving is similar to something known as the Kapitza pendulum, which I'll describe in more detail in a second. But the Kapitza pendulum is very well studied, but motivating multiple Kapitza pendula all interacting through some Coulomb action didn't really make sense, except in this context it does. So we can confine particles to one dimension to simplify the system. We use a linear quadrupole trap, and particles will be confined to the axis of the quadrupole trap. And then we use two arrays of electrodes on either side, where opposing electrodes are in phase and adjacent electrodes are 180 degrees out of phase. And so the direction of the electric field perpendicular to the quadrupole axis cancels, and you just end up with something of a form of a pseudostatic longitudinal standing wave in the axis of the quadrupole. This is just looking down the quadrupole. We showed the actual setup. The details aren't too important. Here's a couple of 35 micron glass beads, and they're charged and they all oscillate and bounce around. And so the question was, how do they behave? And so by tracking the particle motions, you can just develop a simple picture of the dynamics. And basically, unsurprisingly, for a small a, the driving amplitude of the electrode arrays on either side. For 0A, nothing happens. As you increase A, you get some oscillation. What you're seeing is an oscillation in one dimension, and this is the phase plane of that oscillation for different values of A. And at some critical value of A, the dynamics change. And then if you keep increasing A further and further, you can end up in a propagating state, and this is similar to any type of driven system where small, maybe just the force-driven pendulum, small driving, you have local oscillations about some equilibrium point, and then as you increase driving more and more, the dynamics change, and then you end up in a state where you might be winding in one direction. So this is the equivalent of that. We've shown a glass bead propagating, well, tried to show, a glass bead propagating in one direction. So these are our experimental data for this kind of simple system. And we did look at multiple particles in this too, but we weren't able to develop such a simple picture of those. So I mentioned the Kapitza pendulum. Let me talk a little more about this, because this is an important paradigm of these systems, and it applies to several other fields of physics also that people might be interested in. So if you shake the suspension point of a pendulum, it becomes a Kapitza pendulum. And something interesting about this system is that when you do this for the right driving parameters, you stabilize the inverted position. And this phenomena is known as dynamic stabilization. I've written the Hamiltonian down as in the frame of reference of the pendulum, and you can see it has this feature that we're interested in. And so this, he published 2 papers on this in 1957. So this is very, very well studied. And so is dynamic stabilization because it's very useful. Where else do you see it? Well, the quadrupole trap, which is also known as the Paul trap, we use to trap our 35 micron glass beads, but it's also, you can't trap a charged particle in a static potential, but if you include time dependence, you can make some effective potential that does have a local equilibrium. So the Paul trap is one example that's used in many different places. High frequency driving of high frequency electromagnetic driving can increase the stability of electron orbitals and reduce ionization rates. I've shown 2 papers, but there's many more on this, and again, this is well studied. And potential renormalization, and I threw this in here for Valerie and Adrian, but they're not here. So this is a simple statement. What is this paper about? Well, it turns out that there's only so much you can do when you make an optical lattice to trap cold atoms, but and you can make a variety of different geometries with different properties. But if you shake the lattice in certain ways, you can renormalize the potential, or get a potential that you otherwise wouldn't have been able to have with just the sort of static setup. So now, what's interesting about this spatial and time dependence, the kicked rotor is a very important model. And so even though the kicked rotor's applications are more in sort of describing analytically other models, it has importance in a variety of places, and you've probably heard of it. And what's great about this model is that you have an analytical solution to the map, which gives you the phase space of a particle analytically in incremental periods of the kicking. This is what it looks like. This is just a picture for you to stare at while I talk. It's one of the first models where people were investigating chaos in some Hamiltonian system. And it also has features that apply relatively universal to driven systems near what's called a separatex. So driven Josephson junctions, this isn't something I'm an expert in at any means, but you can also find people use classical equations of motion to describe the phase of these systems, and you can drive them and end up with similar forms of a potential describing your system. Transport, control, and ratchets, these are people interested in molecular motors, where you set up some periodic potential and shake it in a certain way so that you might be able to do some work on a small system. So this is kind of where you see these things. And then, as the last slide in the motivation section of this talk, I just want to mention long-range interactions, because they're prevalent in nature, at least in the way I've defined them, or people define them. And you're not going to drive a gravitational system, so we're not interested in this really, but this is just an example of its prevalence. Usually, a long-range interaction, or the range of an interaction, is described by some characteristic length of the interaction potential. This definition is a little different, where the potential is proportional to 1 over r to the gamma, and gamma is less than equal to the dimension of the space the system is embedded in. Technically, any power law has no characteristic length scale and is considered long range, at least in the way that people usually talk about them. But this tells you something about the extensivity of the problem and whether or not your potential, you can create a thermodynamic limit that makes sense, and I'll talk about it in more detail later. But aside from charged granular material, where in gravitating systems, where might you find these types of interactions? Well, so non-neutral plasmas, where you have reduced screening, you might approach the Coulomb interaction, which obeys this particular form. And so the point of, I've just stolen these videos off of the non-neutral plasma group at University of California, and you see that there's some qualitatively similar behavior, but there's also a rich variety of behaviors, and these are experimental videos of some if you're interested in these, we can talk about them later. But so if you were interested in driven plasmas, this might apply. So okay, with kind of overall motivation, let me just skip through really quickly what I covered last time, just to develop some context for the more recent work. So the single particle dynamics in the simplest form of one of these potentials. So here A is the driving amplitude, and I've written down equations of motion that include dissipation that's linear in the velocity. And with these equations of motion, you can make some bifurcation diagram. Let me tell you how this was made, because this is important in understanding these systems in general. I'll come back to these features later, actually, when we talk about the multiple particle case. I mostly just want to talk about the Poincare sections for a second to define them. So if you have a second order differential equation with time dependence that describes your system, you can turn it into 3 first order autonomous differential equations where you write your time dependence in this very trivial and kind of silly way. But this x3 is time, so derivative of time is just 1. What's the point of this? Well, it tells you the dimensionality of your full phase space. And if you're interested in dynamical systems, this is a very important thing to know, especially because stretching and folding, when you have chaos, it's intimately related to the dimension of the phase space. The ways you can tie knots in different dimensions is an interesting problem. So in 3 dimensions, if we look at this in the Cartesian coordinate space, these are the position, the velocity, and time respectively. So a Poincare section, and we have some spaghetti complicated, maybe chaotic or transient motion. Poincare section is just simplifying this picture, and we're just going to choose a value of the time, let's say pi or something, and we're going to draw a plane at that value of time and plot the trajectory as it passes through it. Just the points where it intersects this plane. That's a Poincare section. Because we have periodicity in time, x3, and space, we can imagine this on the toroid, and then the Poincare section is one of these slices. And if we sweep the slice through the toroid, you can generate, so let me finish that explanation. We're going to take the Poincare section, we're going to project it onto the position axis, and then we're going to plot what we have for the value of A that was done for. We do this many times with many different initial conditions and for many different values of A, and when you stack them all together, you end up with a bifurcation diagram that depends on the choice of Poincare section. But the point of this video is that the overall behaviors don't. The chaotic regime doesn't change depending on the choice of the Poincare section. The types of bifurcations you have don't change. And this is just a histogram showing that the density of where things end up for different initial conditions. And last time we talked specifically about the types of bifurcations. So I'm going to skip over all of those and skip to a point that's relevant later in the discussion, which is after a period doubling bifurcation, you end up with chaotic trajectories. And the point of these pretty pictures here is to say, when you have chaos in a nonlinear system with damping or whatever, it's often described by a strange attractor, which is a fractal in your phase space. And so you have random motion in the sense that initial conditions close together separate exponentially as time goes on, but it's restricted to some kind of well-defined area of the phase space. And actually for specific systems, ones that obey what's called Small's axiom A, you can approximate them with an analytical map. And so you can actually say something, you can define ergodicity for a small set of systems that exhibit stretching and folding in the phase space. The stretching and folding is what gives you your chaos. And so, why do we care about this? Well, ergodicity is important for understanding the statistical mechanics of systems, and if we're interested in a large number of bodies all interacting, this seems like a reasonable way to approach and attack these systems. But right now, I mean, if we only have one particle, you don't need a statistical mechanical description. So keep this in your mind, and we'll return to this idea a little bit later. But now let's talk about the multiple particle dynamics, which exhibit some similarities. By multiple particle, I just mean, let's take a bunch of charged particles, classical charged particles, put them in a potential of the same form, with the same dissipation, and let's see if anything interesting besides kind of silly video appears. So let me make a couple of definitions. Capital N is the number of particles. We'll call little n the number of periods over which you make the system periodic, which is going to be our way of approximating an infinite system. And so n over little n is going to be a concentration. I've written down the force and not the potential for a reason. The potential doesn't converge as I've expressed this problem, but the force does. So we'll talk more about the potential in a little, but for now let's just focus on getting the equations of motion and solving them for some trajectories. And the reason I've shown this is the details aren't too important, but the force in this approximated infinite system where you make periodic boundary conditions, you can dress the force from the Coulomb interaction with some additional term that depends on these Pauli gamma functions. It doesn't matter, but it also depends on the radius. And so by dressing the interactions, you approximate your infinite system. And with this, you can make some equations of motion. But this is the important idea here. So let's just define our parameters. We'll set the charge equal to 1, the mass equal to 1, same damping, and we'll set little n equal to 1 so we only have integer concentrations. Generate some pictures. And again, I'm just going to kind of zip through this and point out the important things, which are, regardless of the many different things you could analyze in these pictures, the important features, there's two important features. One is that the number of attractors, there's one here and one at the seam of the periodic boundary conditions. The number of attractors depends on the parity of n. So we have 2 for capital N equals 2 and 6 for capital N equals 3. And we showed that this has to do with the symmetry of the potential and the symmetry of n. So if you wrap your periodic system into a circle, draw a line that bisects the circle, just telling you where the nodes of the potential are, then we showed that this clarified why you have a number of attractors equal, or that depends on the number of particles. It's just this symmetry relationship. And so the other thing we showed was that at some point a certain type of attractor squishes out the first type that you appear, and basically the whole point is that there's a discontinuous transition in the value for A of which the first bifurcation occurs. And so this is something we talked about in detail in some paper, and these are important features of these models. But what I want to talk about is something a little differently, which is more to do with the statistical mechanics of these models. So if we're interested in having a large system of this type and looking for some transition that occurs, and maybe we don't have access to these complete bifurcation diagrams that tell us so much about what's going on, well, if we're looking for different kind of modes of activity, then there's probably some transition between them. And so you might look for the peak of the fluctuations of some value. So specifically, we look at the fluctuations of the kinetic energy. And the idea is that when you have things like critical slowing down, and you're about to go through a transition, the form of the potential minima that your system sits in has to change its shape to accommodate, or this is the transition. And as it changes shape, it flattens out at some point, and the system can be sensitive to external perturbations. Here we have no external perturbations, but it turns out that transient motions play plenty good enough role. So now we take some pathological choice of concentration. And 20 particles in 3, it's a concentration of 6 2/3. And we reduce Q to allow maybe for some more random motion. And generate what can no longer be called a bifurcation diagram. And the point of showing this is that there's different qualitative regimes here. Now, I talked about a pendulum winding in one direction. Let me just say with words that this regime here is a bunch of particles undergoing small local oscillations at some point. And then something happens, and then on this side, they move into this attempted propagating motion. So attempted propagating because unless they're all propagating in the same direction, they're going to be bouncing into each other. These white streaks correspond to a point where the computer can no longer solve the equations of motion because the collisions are too violent and it can't resolve them. So I've said that with words. What does attempted propagating mean in a more quantitative sense? It means that the velocity distribution changes. Here it's peaked about 0, and then at a certain point it's peaked about 0 with 2 additional peaks on either side of 0. So can we pick up this in the fluctuations? Well, I mean, kind of is the short answer. We look at the squared fractional deviation, which is just a measure of the fluctuations, it's dimensionless, as a function of A, and some kink does correspond roughly to this, but it doesn't fit with your normal understanding of what's going on. But it turns out that if you look at the fluctuations in the Poincare sections, then you do find some peak in the fluctuations. So E prime is just a notation, the kinetic energy in the Poincare sections only. And so why is this? It has something to do with correlations and the time scales on which you observe things. And in statistical mechanics, you usually assume that your observational time scale is very long compared to the dynamical time scale. And so it turns out that the Poincare sections are a very convenient choice of an observational time scale. And so this also kind of works for smaller n, picking up some of the transitions. I guess this is just a simple example. And so I think that this is an important idea that's omitted. It's nothing too complicated, but it's when you're looking at dynamical systems and statistical mechanics, you have to choose some time scale, and this is a nice one. And there might be some more interesting subtleties here. And so in order to kind of investigate these things with a little bit more of an analytical approach, we wanted to set up a model where we could explore some things like the fluctuations and how they depend on the observational time scale and things like this. And so we did set up a simple model, and we kind of didn't even make it to the driving because the interactions being long range, there was enough to explore. There was enough to explore just in that case. And so I don't want to say they're not well understood. I guess they're not. They're pretty well understood, but there are some difficulties in treating them that make for interesting properties, and they have a lot to do with the dynamics that I've shown. So let's just talk briefly about what the problems in treating these with your standard statistical mechanics is. A well-defined thermodynamic limit means means that as n goes to infinity, v goes to infinity, but in a way so that this ratio is constant. For the Coulomb interaction, for instance, which is all we're going to work with, the gravitational interaction, it's the same. This is no longer a constant, it goes to 0 because v goes to infinity, more like n squared. So they're not extensive. And another problem is they're not additive. So usually you assume that your canonical ensemble is justified by taking some small subsystem of a larger system, and the larger system is the heat bath, which allows the energy to fluctuate in the smaller subsystem. But with long-range interactions, you don't have additivity. You can't approximate a larger subsystem by the sum of the energies of two small systems. So when you sum two smaller systems, you get some additional energy that depends on the boundary between them, let's say. There's a variety of ways you could add them together. But this is small compared to the bulk. When you have long-range interactions, everybody cares about everybody, and you no longer have additivity. So with that in mind, let's completely ignore it and solve for the canonical ensemble anyway. Turns out that, at least in the model, we're going to solve the canonical ensemble and the microcanonical ensemble are equivalent, and you can prove this, but it's much easier to work in the canonical ensemble. So I'm not going to prove that they're equivalent. I'll just sort of say that and take you through some very simple physics on the, well, first let me define the model, I guess. So what is the model? Well, if we're interested in these, maybe some large periodic system where you have particles oscillating at some minimum of a shaken field. Anyway, this is not so different than a lot of pendula. If you were shaking them, maybe they would be Kapitza pendula, and you'd be interested in the statistics of multiple Kapitza pendula interacting. So what are the interactions? Let's consider charge bobs. But we're not going to shake. We're just going to look at the small angle case, and we'll define x to be the horizontal axis in this model. And so with the small angle approximation, we can express x of the ith particle in this id, where d is the distance between them, and L theta, where theta is the angle from birth. We'll rescale the system to make it fit into 2 pi. And so now the positions of the ith particle look like this. We're just going to call this rescaled angle phi, just as a notational choice. But this is important. We're gonna let phi be large. So we're gonna make the pendula. We're gonna make them really long, and we're going to stuff them very closely together so that this is proportional to n. So phi can be large and cover the system. This isn't because theta can, it's because of this particular limit. We're going to make some approximations that make this analytically tractable. So and so this is one of the approximations, the long pendula close together. So this is just a coordinate transformation. It's nothing amazing. The coordinate transformation is a simple twist map. Here are the positions of the pivots in x, and here are the positions of the pivots in phi. This diagram's purpose is just to show you the twist map that is the coordinate transformation. And we're also going to make an approximation. We're going to make the pendula bobs flat, and we're going to stack them up together. And that just changes. That allows us to write this in terms of an actual one-dimensional problem. And so that will come into play when expressing the Poisson's equation. So this, we can write down the density, just the sum of the delta functions, or the positions, and we're going to include a homogeneous background charge of the opposite sign. That's pretty normal when treating these systems. And then we write down Poisson's equation for the one-dimensional case. And now we're going to make our last approximation, which is the worst one, which is we're going to smear each of these bobs out over a large portion of the physical space, which amounts to truncating the sum of the delta function. And so the idea is not to develop an exact model for charged pendulum bobs interacting. The idea is to pick up on some qualitative behaviors qualitative behaviors of these long-range interacting systems. And so, as I've expressed it here, we can, if we truncate the sum in the worst possible way, and we just take the n equals 1 term, the 0th term is canceled with this constant here, then we can solve Poisson's equation for the potential. And we end up with a difference between the two angles and an extra phase that depends on the indices. In the x-coordinate frame, this is just the xy spin model. So we're just looking at a different coordinate frame of the xy spin model. And so when we first made this model, that was like, oh, you know, darn, that's not too interesting because it's just the xy spin model which people have been studying forever. But we actually can elucidate some behaviors of the xy spin model in this coordinate frame. Solving the partition function in phi is a pain. We use coordinate transformations to make solving these things easier. But the non-equilibrium dynamics actually might be easier to look at in the case of phi. So I'll explain that in a second. Anyway, I've written down the Hamiltonian, and you'll notice that I've included a scaling of 1 over n. This is to make the thermodynamic limit behave in the normal way where n over v is a constant. And this has, well, this scaling tells you something immediately about the way these systems behave, which is this. If you take the thermodynamic limit, then n gets large and pairwise interactions are vanishing. If pairwise interactions are vanishing, then correlations between particles are vanishing. So what do the particles care about? They care about the mean field. And you can extrapolate this further and actually kind of just based off of the long-range interactions, you can describe how something like a galaxy forms, which is known as a core halo formation. And it happens because if they only care about the mean field, if you have mean field fluctuations, then some particles will be in the opportune locations of the phase space to pick up some of the energy from the mean field fluctuations. As they do, the parts of the system that belong to these particular fluctuations, parts of it have to cool to conserve energy, and this actually continues in such a way so that part of the phase space becomes very cold and part of the phase space becomes very hot. And this is a particular type of form of broken ergodicity that also makes these systems challenging. Okay, so with the Hamiltonian we can solve for the partition function. Doesn't matter if you do it in x or phi. There are some subtleties in equating the two at a certain point, but really this is just for people who are familiar with these models. You end up with an expression of the free energy that looks like this, and by maximizing this term, you can graphically show that there's a phase transition. And it's the second order phase transition, and it happens at beta, which is now 1 over kBt, not the damping, happens at this value of 2. And so this is what's very well known about these systems. So where does our work come in? Well, the non-equilibrium behavior, which is under some debate. What happens when you start the system with repulsive or anti-ferromagnetic interactions? You start it in a cool state or some low energy state. You end up with oscillations initially that result in 2 clusters, which you'll see form here and here in a second. And the stability of these clusters is what's debated. And there's a variety of ways you can argue different points on their stability. They sort of come together and then break apart and move around. And if you look at this picture in the phi coordinate frame, if you just randomly choose positions of particles in x, here are the clusters forming in the x phase space, and here is just complete disorder, and wow, that's a terrible axis label. Sorry about that. So basically in phi there's no order, just for a random configuration. This looks like it doesn't obey Louisville's theorem, but it does, because the phase space is actually 2n large, and so they're still following some curve of constant energy. It's just disordered in this picture here. But for a particular choice of phi, it doesn't change much about x. They're a little more well-ordered, so the mean field oscillations start smaller, so we start with a smaller amplitude. But we're going to order phi according to these rules here. And just so that this is the order. And in phi then, the picture looks similar to x, but with twice the periodicity. And it turns out that you do end up with clustering in phi here. So why is this helpful at all, or why is this useful, or even interesting? If the stability of these clusters are debated, what can we say about the stability of these? And this is the interesting point, which is that for some, so here is just a histogram of the positions to show you that 4 clusters appear for some range of time. Here we've color-coded them if they're ordered. It's just a way of looking at the system. We've color-coded them according to their index. They're ordered by their index. So here's their order in phi, and this is just the time axis, so we plot their order as a function of time. And we start with n small, there's nothing, there's no order. As n gets larger, we start to see these clusters, which essentially are, so the clusters form, and so some order persists in the labeling for some longer period of time. And as you increase n more, these exist for longer and longer periods of time. And part of what's interesting about this is, so now I've shown n equals 100, the time scale is reduced by a factor of 10. So the initial mixing happens quite quickly. But then what's fascinating is that some index separation occurs, which then stabilizes the clusters. And the more n you have, the stabler they are. For long-range interacting systems, you can have what are known as quasi-stationary states, where the system is approaching thermal equilibrium, but it can't get there quickly because it can get trapped. Well, basically the amount of time it takes to approach thermal equilibrium can diverge as you increase n. And so these are called quasi-stationary states. These are not metastable states, which sit in some local minima of the potential landscape. They are this other type of state that only happens when you have long-range interactions. And so what we've shown here, what this picture shows, is that in the phi coordinate frame, these are decidedly quasi-stationary. In x, it's debatable whether or not the clusters that form in x are quasi-stationary. So this hasn't solved the problem of what's happening in x, but it is interesting to say that the stability of the clusters in phi are quasi-stationary, and that's certainly true. So we're working on publishing some of this stuff. And so I've shown a couple of different things here. I kind of want to unite some of these ideas. We started with multiple charged particles in this type of driven system, talking about the parity dependence on the number of attractors, and something that the bifurcation that depends on n. So really kind of the overall and quasi-stationary states which depend on n. So everything depends on n, and it's a very important number in these systems. And so for future work, let's kind of tie this together. Basically, when we approximated our infinite system by making periodic boundary conditions, dressing the force to account for this pretend infinity, we transients went away relatively quickly because you just dress the interactions. You don't actually have a large number of degrees of freedom that can put you into a quasi-stationary state. If you think about the same concentration but include more and more of your mirror systems that you're summing and actually give them real degrees of freedom, you might end up in a quasi-stationary state for a big enough system. So what I think it would be interesting would be to study, okay, we find the equilibrium behavior by dressing the interactions, and then maybe we can say something definite about how a quasi-stationary state is going to approach this depending on where you started from. The problem with long-range interactions is they don't approach equilibrium in this collisional way because you don't have collisions, you don't have any particle correlations. The particles only care about the mean field. And so it's not the Maxwell-Boltzmann distribution. You use something called the Vasilov equation to find the single particle distributions, but it has an infinite number of invariants that depend on the initial conditions of your system. So maybe by looking just at smaller systems and finding equilibrium for them, you can say something about how the quasi-stationary states approach them. And if you wanted a really analytical understanding, if you've condensed your problem down into one with a few number of degrees of freedom, well, as I mentioned, you can describe the random motion probably with some strange attractor, and you can start defining things like ergodicity and maybe actually put together a full statistical sort of mechanics model of what's happening. Anyway, these are just some loose ideas based off of this work on how to, if you cared enough, how you could start putting the pieces together. And with that, I'd like to thank Dr. Wu and Jeff, who've worked very closely with me and essentially taught me how to write, and many other things. Chris and Adrian and Dennis for their immense amount of support and patience, and just a tremendous amount of information. And Anand for indulging in all sorts of curiosities. So thank all of you, and thank NASA for the money and the computing power from the VACC and the whole physics department and everybody for their support in this.
Nice pictures. Now we can take some questions. Yeah.
So you said that this could be used to clean to get the particles off the solar panel site. So why do we want to use this rather than say like a windshield wipe block?
Yeah, because if you wipe the surface, you'll abrade it, and that.
Oh, it's even some gentle.
Yeah. Well, so gentle is. Yeah, I mean these rocks are hard, and if you scratch your glass, you reduce the efficiency.
That's it.
Well, another thing, this is for NASA applications. Presumably, we will go to Moon or other planet. There's no water there, so you have to find other way to clean the surface.
Yes.
Yeah, this is hard to do when you have water because, I mean, water causes all sorts of problems with discharges. But yeah, so it's mostly an application for extraterrestrial.
They're also looking at this. There's a big project at Boston University that look at this for arid environments.
Oh, right, for arid, yes. Yeah, right.
Going back to the solar cell, it looked like the mass flow is preferentially in one direction, not a bifurcation.
Yes.
Is that a complex potential, or is that a symmetry breaking because of tilting? Or
So in the actual video of the cleaning, yeah, so I didn't say this, but that, if you change the, if you have a phase separation between adjacent electrodes that's less than 180 degrees, you actually get this kind of traveling, rotating field. So you can
more efficient cleaning that way.
Yeah, but it's also harder to make. So there's arguments about payload restrictions, and if you you have to include more stuff anyway. But yeah, so that particular one was what's called a traveling wave flow.
Any other questions?
You were talking about those clusters. I can't remember exactly what you're but you're talking about, you have these plots that, maybe you can go back to slide, but you have
Yeah.
these plots that were oscillating up and down and yeah, those.
These or
So-
these?
Yeah, the next, or maybe it's back, no, yeah, those
These.
ones, yeah.
These ones.
So, are those rotating in some third axis, or is that just an optical illusion?
Oh no, I think
So-
there's definitely some structure there. Yeah, absolutely. I think the loosest argument is that if there's structure in some ordered case, then maybe there's structured in, this isn't ordered, but, so there's structure in X. So if you just have this twist mapping, there should be some structure. The point is though, that the structure isn't in the angles. It's in some, maybe you can start slicing, taking planes of the higher dimensional full phase space, and you could have some structure that looks coherent somewhere in there. But just the point is, there is probably, but the structure isn't in phi. You don't have clustering of the angles.
If there's no further questions, so the public can leave and the committee will start.